So welcome everyone. Welcome to today's session. I'm Allison Cheng. I'm a software engineer from the real-time team in DoorDash. In today's session, we're going to talk through Flink and Delta, and I'm going to show you how we use Flink and Delta to drive the real-time pipelines at DoorDash. This is today's agenda. I have 4 sections. The first section, I'm going to briefly talk about us, DoorDash, and our team, real-time team. Second section, I'm going to talk about why we choose Delta Lake, and further why we choose to use Flink with Delta Lake. Third section, we're going to talk about some details of how we use the Flink in our real-time pipeline. And the very last section, I'm going to talk through some examples and lessons we learned in this journey when we tune the performance of our real-time pipeline with Flink and Delta. Now let's start. About us. So as you all know, we are DoorDash. Actually, I have a question for all of you. By show of hands, can you tell me how many of you have used DoorDash to deliver food? Wow, I'm so proud. So now, by show of hands, I want to know how many of you have ever used DoorDash to deliver something else rather than food? Wow, cool. Well, I want to let you know that we are not only for food delivery. You can do the grocery shopping with DoorDash. You can buy some flowers and deliver to your mother to make your mom happy. For me, I also order the pet supplies for my cats to make sure she won't complain at me. I want to point out our mission. We are not only for food delivery. Our mission is to grow and empower the local economies. And in order to fulfill our mission, the real-time events from our end customer are super important for us to gain the insights into our business. By saying that, I mean we need to deliver the real-time events accurate and in time. Now I want to talk a little bit about us. So as I said, we are the real-time platform team at DoorDash. Our team, we own the real-time infrastructures that process petabytes of data per day. Our team's mission is to provide our data user or applications with the platform to capture, access, and create the real-time insights. Now let's talk about some motivations, why we choose to use Delta Lake, and further why we choose to use Flink with Delta Lake. So as you may already know, Delta Lake, it is scalable. Right now, more than 2 zettabytes processing per day through Data Lake. Data Lake is also very popular. There are more than 1 billion downloads per year. Data Lake is also very reliable. There are more than 10K of companies using Delta Lake in production. Delta Lake is also open source. There are more than 500 contributors contribute to the Delta community. Now I also have a graph to show you Delta Lake's large and mature ecosystem. For example, you have the freedom to choose. For example, the processing engine, you can use Apache Flink, or you can use the Apache Spark or Beams. Now let's talk about why we choose to use Flink with Delta Lake. So some of you may already know, actually Delta Lake started with Spark earlier. Much earlier than Flink. We choose to use Flink because we already have Flink integrated into our real-time platform. We do have the automated process, and we have the mature ops toolings. We also have the runtime Kubernetes-based runtime environment, and we also highly invested in our Flink infrastructure. As that being said, it actually requires a minimum effort for us to integrate to Delta with Flink directly, compared to rewrite whole our workflow with Spark again. Another reason we want to start with Flink is because at DoorDash, we also have other teams who are using the Delta, who are using the Flink. So we also want to support those teams to be able to read from or write to the Delta Lake. Now let's dive deep into some details of how we use Flink. Before that, let me recap a little bit, just in case you don't familiar with Apache Flink. So Apache Flink is an open source streaming processing and batch processing framework. Flink is designed to be the low latency and high throughput data processing engine. Flink is also stateful and fault tolerant processing engine. By stateful, I mean Flink, it do have the internal built-in mechanism that it can store the most recent process state to checkpoints, so that whenever you have failures, you're able to quickly recover from the previous checkpoint to be fault tolerant. Now, I have a graph to show you all of the details of our real-time pipelines at DoorDash. I highly recommend if you have interest, I highly recommend you to read our DoorDash touch blog. In this touch blog, we illustrate all the details of our real-time pipeline. However, for today's session, we're going to mainly focus on Flink and Delta. So I did some homework. I simplified this workflow for you. So basically, our workflow is we collect the real-time events from two sources, external and internal. So external can be the mobile apps or websites. Internal, we also have some internal service that generating the real-time data. So after collect those data, we publish them to Kafka topics. After that, we have different Flink applications that read from different Kafka topics, and then we're going to upload those real-time data into S3 in the raw Parquet file, in the raw Parquet format. I want to mention today, we are operate at the petabytes of data per day level. So I want to talk about some challenge we meet with the previous workflow. We actually do not have the ACID guarantee at scale because the Parquet file by itself, it do not guarantees to provide it a consistent view of the data. Currently, we only support one single writer, and we do the append only when we upload the data into the S3 Parquet. We do not have the ACID guarantee, so we cannot support multiple writers or modify on the data we already put there. We're also facing some large numbers of small file problems when we upload the file into S3. We already try very hard to select the perfect smart partition column when we output S3. However, sometimes we still have this problem. Without the ACID guarantee, we basically it's very hard or almost impossible for us to rewrite those small files to merge them into the large files. The third problem, the fourth problem is actually we have an extra step. We need to move the data. So first, we produce the Parquet file to S3, and we have an additional step. We load those Parquet file into our query engine. Later on, a user can query those data. Now let's talk about how the Delta helps us to solve all those challenges. So Delta by itself, it guarantees the ACID transaction. Their solution is based on Amazon S3 and the DynamoDB. And also, with the Delta Lake, we can support any number of writers concurrently write into the Delta Lake. For the small file problems, Delta Lake have some out-of-box solutions. For example, Optimize, which can help you to compact the file into a more desired size of file. And this one, you can run it separately in the background. It won't block your real-time data ingestion, and also with the ACID guarantee. The last problem we have, because we can use the Flink Delta connector when we upload those files to S3, it's also a commit to the data lake. So we do not have to have an extra step to load the data into the query engine anymore. I want to also mention like Delta Lake also have the z-order, which can, like after we load the data into the S3, it can help us to improve the data layout on the S3 to make the query more efficient and also with the asset guarantee. Now let's come back to our Flink application. So majorly, like our Flink application have 3 layers. The source layer, where you define like where you read the data stream from. And also the second one, the transformation layer, which you define the transform logic that you want to apply on top of your data stream. The last layer is the sink layer, where you define like where you want to output your data stream to. So in our case, like the external file system we choose is S3. Now I want to show you like it is actually very easy for us to switch from the streaming file sync to the Delta Sink. We can keep the source and the transformation as it. The only thing we need to change is the third part, the sync part. So by changing to the Delta Sink, Delta Sink is going to responsible for upload the Parquet file to S3 and also commit to the data lake. Well, it is actually very easy to use it. However, like I think you all like has the experience like whenever you want to push your like system or pipelines to some limitation, for example, like operate at a large scale, it is actually not super easy. You're going to meet a lot of like difficulties. So today, like I want to jump into the performance dive deep section. I want to show you some like improvements, some stories we have when we tune the performance, and some lessons we learned with you today. The first one I want to talk about is the small file problem. So small file problem is not, it's actually a very common problem. It's not related to Flink only. If you are using this Spark, you may also facing the same problems. So when we set up our Flink application and upload the S3 file, upload the Parquet file to S3, and also commit to Delta Lake, we actually observe that Flink is actually generating about like 2 megabytes size of files on S3. So let me give you an example. So say we have some events. It's going like, and we also use some like a partition columns to do the partition writes to S3. So each of the file-based sync operators going to write the partitioned file to S3 and further split into the park files. I put a screenshot here to show you like for some events and for some particular partition volume, this can be like different sync operators upload to S3, like doing some like a Flink checkpoint interval. I want to point out like the downsides of having too many small files on S3 is actually it is bad for the write performance when you write to S3. Additionally, it is also like cause bad query performance when some user later on want to query this data. Why it is like have the bad impact on the write? Because the Flink need to like maintain unnecessary amount of the S3 connections in order to publish those small files. For the query performance, why it is so bad if we have small files instead of like a desired file size? Because like it put overhead on the query engine when you try to list and load those raw Parquet file into the query engine and try to fulfill the user's query. Well, the first solution we had is we adjust the Flink checkpoint interval to get the more desired file size. For example, like for some of our pipeline, we increase the checkpoint interval from 1 minute to 2 minutes in order to get more larger file size. You may have the question like, what file size is small, what is more desired? So I pull a table from the Databricks website to show you like for different size of table, like what can be the desired file size. I think this is a very good guidelines that we can start from and then tune like each different pipelines. Well, after we tuned the checkpoint interval, we're still like facing small file problems, and that is because like the traffic pattern we have. I put a screenshot on the top right. This is a 7 days view of our traffic volume for some of our events. As you can see, like sometimes we have the higher traffic, and sometimes we have the lower traffic. So with the previous like fixed checkpoint interval and fixed of the Flink compute source, so we may able to get the desired file size when we have the peak traffic. However, when the traffic decrease, we again start to see relatively smaller file size like at S3. So our solution is that we turn on the auto scaling. For our case, we are using the Kubernetes, so we enable the Kubernetes HPA and plus the Flink reactive mode. This way, like we can get the suitable file size even when the traffic is low. And an additional benefits for this is keep cost efficient, because we can dynamically and automatically adjust our compute source along with our incoming traffic pattern. The next one, I want to talk about the data partitioning strategy. So I want to point out like choosing the perfect partition column is kind of like a tricky problem. Because the partition strategy, it can influence both the write performance and the query performance. So sometimes it's kind of like a dilemma, like if you satisfy like the write, maybe you will have a worse performance as the query. I can give you some like extreme case just to demonstrate why I said it's a dilemma. So for example, let's say if you choose like a hard cardinality column as your partition column, you're going to maybe like at the query time you can query faster. However, like it's going to cause like the Flink output a lot of like small files again. So the small file problem come back again. Another extreme case can be like let's say we do not have partition at all. Then we maybe can write to the S3, no problem. However, when you query the data, there's no like additional information that can help the query engine to know like which file we can skip. So the query performance will be impacted. Well, we have like 2 lessons learned when we try to improve the write performance. The first one is to avoid using the high cardinality field as the partition column, because it's going to cause like when the Flink writes to the S3, it's going to physically like split those parquet file into those high cardinality partitions, which is going to cause like the small file problem again. Second lessons learned is like if you already know of like the pattern of your events, you're going to have a lot of like late arrivals. Try to avoid to use the hourly event time as a partition column. This also will generate a lot of like small files because you already closed for that partition. But however, like when the late arrival message comes, you still need to open a file and relatively small files on S3. So if we apply those lessons learned on our partition column, we maybe already solved like the write performance issue. However, like how about how to solve the query performance issue then? I want to introduce a out-of-box solution from Delta Lake. It's called the order. What the order does is it can go back to the parquet file and collocate the related data into the same set of files and reorganize them and also recommit them to the Delta Lake under the async guarantees. I have an example here to show you like behind the screen what the order do. I have a before table here. So this table has 3 parquet files. For example, like the first parquet file, like maybe the item price, the minimum of that is 6, the maximum is 8. Later on, like more data coming in, and Flink output another parquet file, like parquet 2. And in this time, like the new data, like maybe the minimum is 3 and the maximum is 10. Without apply this the order to fulfill like a user's query, we need to load 2 files, like colored in the green into the query engine in order to fulfill user's query. The third one, like marked in the red, will be skipped because that is unrelevant events for this particular query. Now, if we apply the order on top of this table, what the order does behind the screen is going to sort this table by the item price and reorganize the Power Query file and recommit to the Delta Lake. All of that is under the asset guarantee. After we apply the order to the same table, if we fulfill like the same query, we only need to load the one file like marked in the green color again into the query engine. This can help us to improve the query performance because like how many data you need to load and scan to fulfill the query do matters a lot to the query performance. I have two tips for apply the order against the data lake table. First one is like how to choose the order columns. So usually like we want to choose those columns that commonly will be used in the where predicates and the join keys to be the ordered column in order to improve the query performance. Secondly, like if some days like the query patterns do change, you can rerun the order by some other columns in order to improve like better query performance when the query pattern changes. Now I want to show you like our current architecture. So we do have a Flink job that focuses on the real-time data ingestion. And we also have a daily Spark job that focuses on some like a query performance optimization task. For example, like the order we just went through, and the optimize and vacuum. So optimize is the out-of-box solution that the data lake provided to go back to the S3 and combine small files into the like more larger and desired size files. Vacuum is also like the out-of-box solution. After you like do the optimize some of the Power Query file, they no longer being registered to the data table anymore. So vacuum is the one that can go back to there and clean up whichever file is no longer being referenced by the data table. Vacuum can help you to clean them up and guarantee the consistency. Now, in next section, I want to talk about like the transaction support inside the Delta Lake. So as I mentioned before, we have the Flink job, which is responsible for the real-time data ingestion. We also have a daily Spark job, which is responsible for the optimized task. We maybe have some other use case that we want to backfill some data into some table. So maybe we will have a backfill job. And to make the things more complicated, like we also have the users who going to read the table at any time. We also have like ETL job scheduled to read from the same tables. So in Delta Lake support all the transactions and guarantees the asset. So with all of the concurrent write, like you don't need to worry like, will I have like a dirty read or dirty write? It's already guaranteed under the asset transaction to prevent the data corruption. Well, in this session, I want to talk about like how we further improve the Flink write performance, mainly like in the global committer. Let me recap a little bit. So as I mentioned before, like we switched to the Delta Sink. And inside Delta Sink, global committer is the last step when we need to commit to the data table. So you can imagine that we have the new data source coming into Flink, and Flink already upload them into the S3. Those are some like committable files ready to commit to the Delta Lake. Well, global committer is a component that is responsible for commit those committable files to the data table. So the first thing, the first issue we meet is after we running the Flink application a while in our system, we actually observed like the global committer the CPU utilization of the global committer gradually increased over time. So we actually report this to the Delta community, and I want to say a shout out to the team. They do incredible work and support 2 improvements. Today, I won't go into details into those 2 improvements. Those are public on the GitHub. If you're interested, you can go there and check the details. So after they have these 2 improvements, we pull the most related Delta, and we test it in our data pipelines. I have 2 graphics there to show you the before and the after. So that after those 2 improvements, you can see our checkpoint duration can go back to near 0 seconds. And we no longer have the gradual increase CPU utilization anymore. I want to mention this is already merged and released. So if you pull the most latest Delta version, you will already have these 2 improvements with you. Another problem we meet is so we still observe sometimes the global committer can occasionally have the CPU spike. And we further dug deep into that, and we found that is because the global committer is trying very hard to do the Delta log checkpoint generation. I will recap a little bit about what is data log checkpoint. So data log, I have a screenshot here to demonstrate when we ingest the real-time data into the data table, each of the commits will be one of those data log in the transaction log. In order for Flink to read it more efficient, checkpoint is the one that is going to combine all those transaction log into a checkpoint, so that the Flink or other writers, they don't need to replay all of the historical transactions. They only need to read the most recent checkpoint file. So this is actually an optimization task come with the Delta Lake to optimize the read from the Delta log. So we add an option for Flink to skip this optimization task. And so imagine there will be multiple writers interact with the same table. You actually can choose which one you want to do this optimization job. So for example, if in our case, we have the Spark job. We also have the Flink job. So in order to get a more further better throughput of the Flink, we choose to move that checkpoint generation to the Spark job. This way, we can have a better write performance. Also, I want to mention this work is also already released. So if you pull the most recent Delta Flink connector, you will already have this flexibility to choose whether I want to do this optimization task with the Flink or not. I also want to talk about the future work. So after we added the option to skip the optimization, now at our scale, the only time we still observe the high CPU utilization is whenever our Flink job restarts. So whenever our Flink application restarts, the global committer needs to read from the data log. And at our traffic volume, when we reach to millions of log in the data log, we're still seeing 1 or 2 spike, CPU utilization spike. So we're going to continue to work with the Flink community and the Delta community to see what we can improve on this. We do have some potential solutions. We have 2 of them. The first one is try to isolate the global committer to its own task manager by using the Flink fine-grained resource management, or isolate the global committer to its own slot by using the slot sharing group. The second possible solution is we can further optimize the process when we read the data log checkpoint. Now, I want to summarize what we went through today. We choose the Delta because it's scalability, because it's mature ecosystem and supportive community. Delta Lake also have the tools for performance tuning. For example, like optimize the order and vacuum. Delta Lake is also integrates very well with Flink's feature. For example, like we went through the details of like the auto scaling. So today we are processing terabytes of data per day using Delta and Flink. Future, like we plan to process petabyte of data per day. We're going to like continue to collaborate with Delta and the Flink community. That's actually everything I have for you today. Now, thank you.